Hello and welcome to ST118 Statistics and Application Session 2, second part. In this video, we will discuss a little bit more on dispersion measures in descriptive statistics. So to recall our example where our x had values going from 5, 10, 15, and 20. All right, and the frequency count was going from 1, 2, 3, 4. And we had 3, 5 times 3, 10 times 4, 15 times 2, and 20 times 1. Okay. And we were saying that the bars that you see frequently in textbooks, they are just extending the visual representation, but not additional information, because the information is just communicated by the height of the point. In fact, the x point, just one point on the y-axis. Okay, and through this example, we would like to calculate the variance of the data here. Okay, so let's begin by defining what is the variance. Variance, again, there are two different measures: the population variance and the sample variance. Just hold your horses. It is not exactly the same as what we saw in the mean definition. So for variance, you want to look at, or rather you want to first know the population mean. So we know that it is buried in the DNA of variance definition itself. To know the population variance, and we write it as sigma square, where sigma is the standard deviation. So although in real life we'll use standard deviation more frequently than variance, mathematically we first have variance. We first define variance. Then we have standard deviation by taking the square root of this formula. So instead of writing a huge square root over this whole thing to define standard deviation, we just work step by step on variance first. So the variance itself is now in plain sight, right? And is in this form. It says that we want to measure the difference, means the distance away from the population mean. Remember, population mean is the center of gravity, right? So if you're further away, then the difference is larger. And it can be signed. That means it can be minus on the left side. If you're lesser than the population mean, then it's a minus sign. Or positive if you're on the right side of mu. And because it's center of gravity, mu being the center of gravity, there will be some data, not necessarily 50%, because it's not median, but there will be some data that is less than mu, there will be some data that is larger than mu. And they don't necessarily cancel out. And we don't want them to cancel out. We want to capture the difference, right? Because the idea being, the more spread out they are away from the mean, the center of gravity, there is larger variance. You see that? Yeah. If they are very bunched up on the mean itself, then the distance is 0, right? Then you square it, it's still 0, and the variance is 0. And that's right, because there's no fluctuation, no vibration away from the population mean. Does that intuition get into you? Okay, so mean is the center of reference. if you think about the data as vibrating, right, off the population mean, yeah, so sometimes left, sometimes right, the larger the vibration, the magnitude of the vibration, the larger the distance, right? And if you square it to get rid of the minus sign, the negative differences, so that vibrations pile up, they don't cancel. So it's like you have a negative 10 and a positive 10, they cancel out. It's as if there's zero vibration. That's not true. In fact, it's even worse, right? So minus 10 and plus 20, they don't cancel out to give you a reduced vibration. They give you an extended vibration, right? Larger shaking of the center of gravity mu. So that's why we want to square it. Of course, we can also take absolute sign, right? You take the absolute sign to get rid of the minus sign. However, mathematicians have decided that using the absolute sign is not nice mathematically, or what they call not differentiable, and there's no ready formulas to deal with the appearances of negative signs and the cancellation of plus and minuses. Not so easy to manipulate the formula, right? So it will just add more difficulty to deriving further insights, mathematical insights from the definition. So it's been agreed to get rid of minus sign, they just square it. Now squaring it and taking absolute value makes a big difference in terms of mathematical simplicity. But squaring it in real life will make the number bigger, whereas absolute sign will keep the number small. So actually, practically speaking, absolute sign is nicer, but not convenient mathematically, right? So that's why we are stuck with having a square. Now remember, the square is just to remove the minus. And then once you have the squares, you want to take the average of the squares. That's all. Finish. Okay, so the average of all the squared differences from the mean is the variance. Let me say again, the average, because it's 1 over n, sum of 1 to n, right? Average of all the differences from the mean, the squared differences, right? The squared differences from the mean is the variance. That's all. Very simple. Okay. And if you take the square root of that variance, you get the population standard deviation. Now, just like at this part, we can also mimic the formula, the rewritten formula as in population mean, right? So as to deal with a histogram or table-like kind of frequency-based data presentation. So then we cannot use 1 to n because it's not in serial form layout. It's in the bin format, right, with the frequency. So we will then use frequency times, you don't frequency times xj, but frequency times the xj minus mu. So the squared differences for xj away from mu, right, is happening fj times. That's what it's trying to say. Okay. And of course, just like before, if we move this inside so that we get relative frequency, then we can also say that this gives rise to j equals to 1 to k bins, fj over n times xj over mu minus mu squared. And somebody, the textbook or the exam question or your project or whatever, can declare, right? Declare this to be p of x equals to xj. So somebody asserts that the relative frequency that was observed in the past can be assumed to be true in the immediate future. So if that's the case, then this gives rise to sum of the j going from 1 to k bins, probability of x equals to xj times the squared differences. You see that this squared differences is the basic DNA, basic concept, right? And the probability is just replacing the idea of relative frequency, which is just a standardized version of frequency. So fundamentally, the idea is still the same. It remains unchanged. But this part, right? This part is also the definition of what is known as the expected operator, x minus e of x. E of x we have seen before is the mu itself, right? Square it, and that is our expected value of the squares of the differences of random variable x away from its mean. So this part is really statistical, mathematical statistics, right? So this part is where the theory and the derivations come in. And there is also a saying about the mean, because expected value is the mean, roughly speaking. So we can say the mean of the squares, right, minus the square of the mean is the variance. So this is the so-called familiar saying. You might not have heard of it, but the square, rather the mean of the squares, you square the variable, the data first, mean of the squares minus the square of the means is the variance. Okay, this is just a prelude. All right, so later on we can just look at this again. Okay, quick calculation. We have 5 times 3, so example here, right? So example, find the variance of the example. So sigma square, or in this case, the variance of x is 5 times, oops, no, it's 3 times, right? Because it's this form. 3 times of 5 minus, earlier on we calculated the mean to be 10.5 in the previous video. So this part is to be squared. And I'm going to just add vertically because it's just easier to present it this way. 10 minus 10.5, still a negative value, but we square it. Then we have 2 times 15, now a positive value, right? Though not exactly proportional. Plus 1 times 20 minus 10. Okay, the whole thing is to be divided by 1 over 3 plus 4 plus 2 plus 1, which is 10, right? So if you do the calculation, you should get something like 90.75 plus 1 plus 40.5 plus 90.25. This whole thing times 1 over 10. So answer is 22.25. So far, so good. And of course, we don't forget our very important working definition, because it's the sample that we will be working with mostly. So sample variance. And here is a big difference from the way we treat sample data than when we were doing our mean calculation. So here, first of all, sample size is small n, not capital N. Secondly, we also base our concept of sample variance on square differences, or rather having some sort of a average of the square differences. But when we are collecting sample, right, we need to make sure that our sample variance definition doesn't involve mu. Because if it does involve mu, then in practical terms, oftentimes when we carry out sampling, we measure a small set of randomly selected data. We oftentimes don't know mean itself, the population mean. So how do we calculate sample variance if we base it on mu? Cannot. So we have to use a unbiased estimator X bar, right? So it is unbiased because it neither tends to be larger than mu itself nor smaller than mu itself. It will jump probabilistically because it depends on your random sampling, but it will not tend to be larger, tend to be smaller. And as you increase sample size, it tends to be closer and closer and becoming more and more like mu itself. So that when your sample size is as large as capital N, you have captured everything, right? So that's the way it goes. And here is the biggest difference. In order for S square itself to be an unbiased estimator of sigma square, because we would also like to calculate the sample variance and then say, well, this looks like a good estimate of sigma square. Just like we calculate the sample mean and say, well, let's just pretend that sample mean is approximately the population. We know it's not exactly the same number, but we know also that it's not far off. We would like that property to be held true also when we use sample variance to point estimate sigma square. Okay, sigma square involves knowing all the data values and calculating population mean. So that's like you basically know all the data measurements of the population. Again, if you recall, interesting population often has very huge number of entities inside, number of measurements to be taken, so that no one individual or even one individual company organization can afford the time, patience, energy, budget, manpower, equipment to measure everything. So our definition of S square, we need it to be unbiased, right? So again, the same property that it neither gives a higher value than sigma square, the true sigma square, nor a lower value. Plus, as we increase sample size, if we do more and more measurements, if we work harder and harder, our S square will tend towards plus minus jumping around, but converge towards sigma square. So that's the kind of property we like. So it's an estimate, but we like this estimator, this mechanism, in other words, the formula. All right, the formula, we like this estimator to be unbiased, to be good. All right, so we have this as the definition. And again, in table form, we can bring this in, and I'm just going to skip this part, right? So go from here to here, and end up having J, the number of bins from 1 to K bins, F of J over N, N itself. This part is relative frequency, not N minus 1. Okay, this part is relative frequency times xj minus x bar squared. Okay, but that's it. All right, just like the mean calculation, there's no continuing into, cannot go into p of x equals to xj and e of x minus e of x squared calculations, because sample is still a subset. Okay, it's not going to suddenly become conceptually, sample is still a subset of population, right? So you can do the calculation in sample, you can do the calculation in population. The two numbers may even match accidentally, coincidentally, fortunately. But the concept remains that sample is sample. It's a subset, small subset even. And the concept cannot be equated or merged with big concepts like probability, which assumes knowledge of the whole population. Expected operator, which applies to the whole population. So cannot, right? So just like in the discussion of formulas for sample and population means. Yeah. So here we have the sample variance, and very fortunately, right, we have this part being the same because it is just frequency times the squared differences from the mean. The mean 10.5, all right, happens to be also the sample mean, because if we treat the data here as sample, remember, we don't know the mu now, we are doing S square now, right? So the 10.5, if we number crunch through, it will be the same. Will be equal to this whole thing, which is 222.5 over 10 minus 1. This one. Okay. Notice the difference now. Okay. That the n minus 1 here has got a little bit of sort of adjustments. So I better correct this. It's not exactly equal. Okay, the correct definition is this. But oftentimes when we are given relative frequency, especially when sample size is also large, we just do the relative frequency and perform this calculation. Notice that this is not really bringing in n minus 1, but bringing in n, because someone else has calculated the relative frequency by dividing by the sum of frequencies, right? But then to do sample variance, we need to be careful here. So if n is small, then this is no longer correct approximation. Yeah. If n is small, then we need to multiply back and divide by n minus 1, just to make sure that the sample variance is calculated exactly. We can calculate sample variance exactly using the definition. We can. But the calculated value is not exactly sigma squared. So you need to know the difference. This part is equal, precisely equal, exactly equal. But S square estimating sigma square is an approximation, is an estimation. So be very clear about that. And when people present to us a histogram like this and change the frequency to relative frequency, because they have, for the sake of presentation, divided by the sum of all numbers, then we need to be careful by multiplying back the sum of all n and then dividing by n minus 1. Okay, so if we want to be exact, then taking the relative frequencies given by other people like this, because they have divided by n, not n minus 1, right? So other people give us the relative frequencies. We can use that relative frequency because we will need to know the sample size. Oftentimes you have to know the sample size. So we will just use the relative frequencies times xj minus x bar squared, the usual. Okay, and then we just multiply by n, but over n minus 1. So this is the adjustment we need. And then you will have exact equal sign. Yeah, okay. Because if you we can move this constant in, right? Yeah. Or rather, we can move the constant out. And once you move it out, then the n will cancel, leaving us with 1 over n minus 1. And the frequency multiplied by the square of the differences from the sample mean will be our definition. We'll match this very well. Then that'll be exact. So just be careful here. But when sample size is large, and this large is by judgment, all right? So like, for example, 100, and your sample variance, you need a precision of only 1 decimal place. Fine. But if your sample size is 1,000, you need a precision of 2 decimal places, also fine. Right? But if you need very accurate 4 decimal place variance, sample variance, and your sample size is in the 10s or 20s, then you better do the adjustment. You see, so maybe you can just adjust. Okay, whatever is the route you take. Where are we now? Okay, at this point, we will find that the answer is 24.722. Larger than the population variance given the same data set, right? That means if we treat this data as population, the population variance is smaller than if we were to treat this as a sample data set. Now, the way I say it is also a bit weird because we don't choose to treat this as population or choose to treat this as sample. We already have decided, all right, that we want to take a sample because the population is too large. So it will have to be sample. We have no choice to treat it as. The reason why I say treat it as is just to, appreciate the differences here. That means given the same data set, sigma square calculation will always result in a smaller number than the sample variance calculation based on the same data set, right? Because we're dividing by a smaller denominator, whereas the population variance is dividing by 1 unit larger denominator, so it will be smaller. So like that. And not surprisingly, we have the standard deviation for population. So sigma population is just going to be SD of X. Sometimes we write it this way just to balance it with variance, VAR, and expected operator. So for population, we can talk about these random variable operators. And that would be basically taking the square root of variance. So sometimes you may see textbooks writing this, which is mathematically trivial, right? Like sigma equals to square root of sigma square. Not very interesting. Why? Well, because sigma square is more readily calculated and easily understandable because you're dealing with squares, not the square root, which typically results in a lot of decimal places. So at this point, if we take an example, sigma will be the square root of 22.25. And if your calculation is the same as mine, you should get 4.717. And again, we don't forget our dear sample standard deviation. Okay, and we don't have a capital letter version. It's basically going to be the square root of s squared. Okay, so using the same example, same numerical example, our S, our sample standard deviation, is going to be the square root of 24.7222. And if I didn't press the calculator buttons wrongly, it should be 4.9721. Yeah? Okay, so like this. Okay, nice. So that takes care of dispersion. Now, another very convenient concept, very nice and powerful and useful concept, is the idea of coefficient of variation. okay, called the CV. So the coefficient of variation, coefficient of variation. In short, it is, we typically just say CV. Sometimes we do say CV of which data, right? So CV for X, CV for Y. So they are basically equivalent. So if you're just talking about one data set, then it's just CV. It's clear that it's the CV for that data. And the way it goes is that the CV for population is defined as the standard deviation, population standard deviation per unit mean value. Right? So this is the ratio of standard deviation over the mean. But it also means that it measures unit average gives rise to how much fluctuations. Nice, right? Because then it is comparable with other CVs. So for example, if we're talking about a stock, right? Stock prices, they fluctuate. And if we want to know which stock is more volatile, and if we say that volatility is risky, all right, so then we equate one with another. Which stock is risky? If it is risky, it's not for me. I like less risky stocks for investment, for example. Okay, so I mean, it's up to individual investor, but suppose if I prefer less risky stock, how do I compare? If you use standard deviation, a change of 50 cents for DBS Bank, which has an average price of $40, is not much. Okay, let's say 40 cents. 40 cents is how much? 10%, 1%. Plus minus 1% is very typical, right? In fact, plus minus 2%, 3% is also not very surprising. So for DBS Bank, the standard deviation can be, let's say if it is 40 cents, then that would sound like very scary because, wow, 40 cents. A 40 cents standard deviation, however, for another stock, let's say city development, let's say $4 on average. Okay. A 40 cents change, that's 10% fluctuation. That's like, wow, my investment portfolio sometimes rises by 10%, sometimes disappears by 10%. That's very, very unsettling, right, for a investor who is seeking less risky investment. So how do I compare city development with DBS Bank? The kind of fluctuation. So you cannot use standard deviation because both, for example, both give you 40 cents of standard deviation. Then we will use the coefficient of variation. So CV for DBS Bank will be 40 cents over $40. That's 1%. Either we put 1% or 0.01. The number can be larger than 1. There's no saying that it cannot be larger than 1. But of course, when it's larger than 1, it's like more than 100%. That's trying to tell us it's a huge amount of fluctuations relative to the mean. Okay. In stock investment, it can mean highly volatile, maybe penny stocks. A change of 1 cent over a 2 cent worth. That is very, 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 very disturbing, right? Because it's a 50% change all the time. So when you divide through per unit mean, you get the idea that it is going to be very standardized. So for DBS is 1%. For city development, it's also 40 cents numerator, but denominator is $4. So result is 10%. Now we can easily tell city development, CV is 10%, DBS Bank 1%. So if I'm seeking lower risk, lower fluctuation stock for investment, because I'm a low risk investor, then the numbers are so clear, like LED indicator, right? Like 1% green light, 10% red light. So I go for the green light. So that's easier to more useful, more telling when we compare fluctuations. So for comparisons purposes, it is much better to look at CV than to just compare the values of standard deviation itself, the sigma itself. And of course, let's not forget, we also have CV for sample, which will be also calculated using point estimations. So S point estimates sigma and X bar point estimates mu, like this. So we can also have an example. So example for the CV, population CV, we have this, which is 4.71. Our earlier calculation here, sigma, right? So 4.7170 over 10.5. If I recall correctly, yeah, that's right. So mu is 10.5. That's going to be equal to 0.4492 per unit mean value. So if the DBS stock price has a mean value of $40, then standard deviation is, under the CV is going to be unitless, but then it's taken as per unit mean value. So the standard deviation and mu will have the same unit as the data itself. So for DBS stock price, it's dollars. Standard deviation will be 40 cents or $0.40. Mean value, $40. So the dollar and dollar will cancel out to give just a index number, or we can call it 44.92%. For the sample, that means if we treat the same data set as sample, then we have the CV estimates as S. Our S value was 4.9721. And the mean was calculated to be 10.5. Again, when our X bar is 10.5, we don't know what is the actual mu. So it's not like these two happen at the same time. Right? They are kind of mutually exclusive in a way. All right, so then if I do my math correctly, it should be 0.473 up 4735. Again, per unit mean value. Okay, and it is certainly good for comparisons purposes. Across multiple, not multiple samples, but multiple populations. So we will have multiple samples, each one taken from each population, and then you can calculate the CVs and then compare the sample CVs for each of the populations and estimate or judge which has higher unit fluctuation. And that would be oftentimes very helpful rather than sigma itself. Okay. All right, so that would wrap up our discussion of dispersions and calculations. In our next video, we will discuss a bonus topic called skewness. And that is also very interesting because it's something that we will examine, or is an aspect of the data that we will examine when we look at regression.